Greetings, geometry students. I hope you have had a good spring break. Hope you found a little bit of time to get some rest and relaxation. We've got a kind of a long road to hoe here as we come back out of spring break, heading toward the end of the year. Got about 2.5 months worth of time without really much time off or many days off or anything like that. So I hope you got rested and have come back ready to work. Please do not fall into the trap of thinking the school year is almost over, it's time to shut it down, because in reality we've got a good long way to go in this semester and a lot of material left to cover. We're going to get started with kind of a transition point in geometry. We have spent the bulk of our year talking about things in 0 dimensions and 1 dimension and 2 dimensions, and now we are turning the corner into 3 dimensions. So we're going to begin with a lesson simply titled Solids, and your objective is the student will acquire a basic vocabulary and understanding of solids. Now, this is a little bit of a deviation away from the things that we have been doing because, as you recall, all of Euclid's work in the elements, the books that were called the elements, everything was based upon 3 basic structures: the point, the line, and the plane. And those were the most basic structures in 0 dimension, 1 dimension, and 2 dimensions. So Euclid himself seemingly left out the possibility of geometry existing in 3 dimensions. Or did he? Okay. The term solids describes a family of 3-dimensional shapes. Now, solids can have a wide variety of properties, so it's difficult sometimes to make statements that apply to all solids. They come in many shapes, many sizes, many numbers of sides, numbers of vertices, numbers of edges, and stuff like that, and we'll get into all of that in the coming days. Okay, but just in general, okay, kind of like with the term polygon, we spent a lot of time talking about different types of polygons, but everything kind of fit under this broad term polygon. Well, we're looking at the same situation. We're going to get a lot of different shapes with a lot of different names and a lot of different properties, but these 3-dimensional figures all fit underneath the term solid. Okay, now just like with many other things in geometry, solids are going to come equipped with their own vocabulary to describe their various parts. Okay, so once again, it's going to be critical, just like it has been all year long, to develop a good vocabulary to go along with the information that we're looking at. Because ultimately, as many of you have found out the hard way, if you don't learn to speak the language of the class that you're taking, it becomes basically impossible for you to try to have any success in that class. Some of you need to kind of turn that ship around, get it headed in the right direction, and realize that, hey, I need to start studying vocabulary for geometry. Make some flashcards, do whatever it is that you need to do in order to learn your vocab. Okay, so let's take a look at some of the basic terms that go along with solids. Now, here is where Euclid's idea of geometry starts to come back into play. All 3-dimensional solids are built out of 2-dimensional polygons called faces. So actually, Euclid's idea of everything in geometry consisting of points and lines and planes still holds true, because it is basically the understanding that all 3-dimensional objects are built out of 2-dimensional planes. Now, this category of faces, okay, these are the planes that build the 3-dimensional solids. Okay, those faces that we just referred to are not often just called faces. Faces is kind of a broad category that encompasses some smaller categories. Now, more frequently, the faces are broken down into one of two categories. Those categories would be bases, okay, and a three-dimensional solid might have one base, it might have two bases, and it might not have any bases at all. How will you know how many bases a solid will have? Well, it'll depend on various aspects of the solid, and we'll talk about how to look at the solid, how to decide whether it does have one base, two bases, or no base at all. The other category that faces are broken down into are what are called lateral faces. Okay. Now, simply speaking, the easiest way to think about it is to just understand that these guys are not the bases. Now, if you are familiar with the Latin of the English language, okay, lateral means away from the middle. Okay, so when we say lateral faces, we're talking about sides. And that's kind of a misleading term because in geometry, a lot of things are sides. So it becomes kind of difficult for that meaning to have any real teeth to it. Okay, so typically what I do is I have geometry students understand what bases are, how to look at them, how to find them, how to determine how many of them there are, and then after you have done that, everything else that is not a base has got to be a lateral face. Now, so if kind of to break that back down, what we're saying here is if you add up the total number of the bases and the lateral faces in a solid, then you have the total number of faces. Now that probably seems a little strange, probably maybe a little bit redundant to have that many names talking about stuff that is kind of very similar to each other. You're not the first person to think that. However, it's important that we learn the difference because there have been plenty of test questions that we faced over the years that basically talk about the differences between faces or bases or lateral faces, and you've got to know the subtle differences in those definitions. Otherwise, you're going to end up answering those questions incorrectly. All right, now back to Euclid. Okay, Euclid said everything breaks down into points and lines and planes. We've already seen how planes do their part in solids. Now let's look at the lines. Everywhere that faces join together, a line segment is formed. Those line segments are what we call edges. Okay, so I picked on a rectangular prism here. Obviously, in a rectangular prism, we have 6 faces of various kinds. Some of them are bases and some of them are lateral faces, and we'll come back to that here in a minute. But the point being, everywhere those faces join together, obviously you have line segments that are formed. Those line segments are called edges. And in this particular case, there are 12 edges. Now, I realize that we're not all artists. Okay, we're in a math class, not an art class, so some of your drawings are going to end up looking a little goofy, and that's okay. Just do the best that you can to get it jotted down. That way, when you're looking back through your notes, hopefully you're looking back through your notes, you will have a diagram to go along with your definition. And again, back to Mr. Euclid. Okay, everything breaks down into points and lines and planes. We've seen the planes, we've seen the lines. Now let's look at the points. Everywhere in your solid that edges join together, a point is formed. This point is what we call a vertex. Now, obviously, in our rectangular prism from above, okay, you can see where our edges join together. There are corners that are formed, and those are what we call vertices. Now, for those of you that are keeping track, this is, I believe, the 3rd different definition that we've had for the word vertex so far this year. And don't worry, we're not done. We're even going to get another definition for the word vertex during this lesson. Okay, this is one of those terms that has been defined and redefined several different times throughout geometry. Now, Before we get too much further into this, there is a mathematical connection, and by mathematical connection I mean an equation that dictates how the number of faces and edges and vertices that a solid will have. There's a connection between them, and that's actually kind of an interesting thing, because if you think about faces and edges and vertices, we are talking about a second-dimensional object and a first-dimensional object and a zero-dimensional object, and they all exist in one equation together. That's a pretty impressive feat. And it's not a well-known equation, okay, but it has been showing up more and more recently on the tests that we've seen, so I figured it's probably a good idea for us to take a look at it. The equation says vertices minus edges plus faces equals 2. This formula is accredited to a mathematician named Euler. Okay, I know his name does not look like it's pronounced Euler, but that is the accepted pronunciation of his name. I have not thought of any kind of an acronym or cute little saying to help you remember vertices minus edges plus faces equals 2. So if you can come up with one, perhaps I can offer you some extra credit or something like that if you can invent some kind of a cutesy saying for the whole class to be able to remember this thing. Okay, let's put this formula to an example here. If a solid were to have 2 bases, 3 lateral faces, and 6 vertices, how many edges does it have? Now, obviously, in the formula, looking at it, very similar to Pythagorean theorem, there are 3 unknowns, and as long as you can plug in 2 of the unknown values, then you can solve for the third one. Okay, so the formula says vertices minus edges plus faces equals 2. Let's see what we know. How about the vertices? Do we know how many vertices there are in this case? Yes, we do. It was given to us in the problem. There are 6. The next variable would be E for edges. Okay, now obviously we're not going to know how many edges there are because that's what the question is asking. Now F is for faces. Okay, let's see how many faces there are. Okay, do not be tempted to say that there are 3 faces, because remember, faces are the bases and the lateral faces combined. Okay, so there are actually 5 faces in this example. So plugging in 6 vertices and 5 faces, obviously we have 6 and 5 in there. And if we add 6 and 5 together, that is 11. And if we subtract 11 to the other side of the problem to get it away from our unknown edges, you'd have 2 minus 11 on the right side, and that is negative 9. So we have negative edges equals negative 9. Well, of course, we don't want a negative variable. We want a positive variable. So we would multiply or divide the entire equation by a negative sign. That would cause sign changes all the way through the equation. And we would have E equals 9. So that is 9 edges. We face problems like this very often where they give us some of the information, vertices, edges, and faces for Euler's formula, and ask us to find the missing piece of information. It's also possible they may give you a diagram and ask which of the diagrams actually matches it up. Okay, and here's one possible look at a diagram, a solid, that would match this particular situation. 2 bases, 3 lateral faces, 6 vertices, and that would give it 9 edges. So there's one possibility. Okay, now a couple of extra vocabulary terms here. Some figures are pointed on one end, so to speak. It's difficult to say an end because they could be just about anywhere. It's not necessarily an end, but some figures are pointed on one side. It is like the entire figure collapses down into a point. When that happens, this location, this point that the figure kind of collapses into, is what we call the vertex of the solid. Now be absolutely very careful. All of the places where edges join together are called vertices. Okay, so each corner point is a vertex. As you travel around, you've got a vertex and another vertex and another vertex and another vertex and so on. Okay, however, there is only one place in a figure that might be called the vertex. Now, not all figures will have the vertex, okay, but it is possible that it might. Okay, in the cases of the figures that do have the vertex, the side that is across from the vertex is what we call the base of the solid. And it's important to remember in geometry that the word base does not have anything to do with being on the bottom. The base can be anywhere. It is a position that has properties that are attached to it. So the base could be on the bottom, as you see in the cone on the left, or it could be on the top, as you see in the pyramid on the right, and it could be anywhere, left, right, front, back, bottom, top, sideways, diagonal. It could be anywhere, okay? But in these cases, the base would be across from the vertex. And you can see in the case of the cone and the pyramid there that the figure kind of all collapses into that singular point. That's why we call it the vertex. Now, on other types of solids, we may not have this pointed location that we can call the vertex. When this happens, typically you have two opposite congruent faces that are running parallel to each other. And when that is the case, your figure does not have one base, it has two bases, and it will be these opposite congruent faces that are running parallel to each other. So as you can see in the rectangular prism on the left or the cylinder on the right, okay, they both have a place where you can say it's congruent. The polygons across from each other are congruent. They are parallel. They are opposite from each other. Those are both going to be bases. And once again, base does not have anything to do with being on the bottom. It has to do with following these properties. Okay, and then we don't run into this guy all that much, or these type of shapes all that much in geometry. Okay, but there is always the possibility that a solid will not have any base at all. Curved solids are examples that would fulfill this description for us, and we run into these more in calculus. Okay, but let's just get it straight. Okay, curved solids are examples of solids that will not have any bases. This is important to note, okay, because again, we do face questions that ask us how many bases certain figures have. This one has none. Okay, now we're going to have formulas that we're going to be following when we are finding various information. These formulas are going to refer to a couple of particular locations fairly regularly. Okay, so we're going to take just a couple more moments and we're going to look at a couple of definitions because we are going to need to know this vocabulary and these locations when the formulas start to arrive. Now here's one we should be very familiar with, height. Okay. Now the height in a solid is going to be found in one of two places depending on how many bases your solid has. Okay, if you only have one base, then your height is the distance from the vertex directly over to the base. Okay, and just like with our measurements of polygons, your height and your base are always going to be identified and always going to be found by the fact that they are perpendicular to each other. Okay, so once again, base will not have anything to do with being on the bottom, and height will not have anything to do with being up and down. It is the fact that they are perpendicular to each other. If your figure happens to have two bases, then height is the distance directly between those two bases. Okay, and once again, height is measured perpendicular to your bases. The last term I'm going to get you with is probably a brand new one to you, and it is the idea of what we call slant height or lateral height. And the slant height is found by connecting the vertex of a solid to its base by moving directly down one of the lateral faces. Now, this is probably a new situation for you, a new definition for you, okay? But it's a very important one when it comes down to the calculations, the math that we have to do for three-dimensional figures. Okay, so slant height or lateral height, those two terms are used kind of interchangeably, so you need to know both of them. Okay, and it is found by connecting the vertex of a solid to the base by moving directly down a lateral face. Okay, and as I said, you will see both the height and the slant height used in volume and surface area calculations. Okay, so that's all we're going to do, just kind of getting our feet wet with some vocabulary. I apologize for the length of the video, but again, just kind of trying to get our feet wet and get ready for the upcoming unit. I appreciate you finding time to get your notes taken care of, and I'll see you in class on Monday.